Right, so now that we've talked about first order ODEs, of course, the next step is higher order ODEs. So that's our next chapter. Higher order equations. Now, specifically, we're going to restrict ourselves to linear ODEs of higher order, just because if you just say ODEs of like second order, or third order, or fourth order, or whatever, well, again, that problem is a little too hard. So we have to restrict ourselves first to just linear ones. So let's, before we get into how to solve these things, there's a little bit of math that we need to discuss that would normally be referred to as linear algebra. So let's just recall that a linear combination of a bunch of functions looks like constant times one function plus constant times another function plus ... plus constant times another function. Right? That's all we mean by a linear combination of functions. Now, I want you to consider the following equation. This linear combination equals 0. Does that have any solutions? By solutions, I mean values for s1, s2, ... up through sn that make this equation true for all values of x. Well, the answer is yes. Solution. If you just make s1 and s2 and ... and sn all equal to 0, then certainly that equation is satisfied. That's what we call the trivial solution. Now, a harder question would be, do there exist non-trivial solutions? And the answer to that depends on the functions that you're working with. For example, if you take, for example, the linear combination s1 times e to the, or no, let's say s1 times, e to the 2x plus s2 times e to the negative x equals 0. Turns out that there are no values of s1 and s2 that would make this true for all values of x, except the trivial solution. But if you take something like s1 times sine theta cosine theta plus s2 times the sine of 2 theta equals 0, well, there are non-trivial solutions to that one. All you'd have to do is say make s1 equal to 2 and s2 equal to negative 1. In that case, you can just use the trigonometric identity, sine 2 theta equals 2 sine theta cosine theta, and then this whole thing equals 0 for all values of theta. Okay, so whether a bunch of functions are linearly dependent or not depends on the functions. Sorry. This is what I'm trying to define here. When you have only the trivial solution, the functions are called linearly independent. And when you have more than just the trivial solution, they're called linearly dependent. So let's go ahead and write down that definition. So definition. Let f1, f2, dot, 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 fn be functions of x. We say that f1 through fn are linearly dependent provided that there exist constants S1, S2, S3, dot, 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 all the way up to Sn, which are not all zero, such that S1 times F1 of x plus S2 times F2 of x plus dot 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 plus Sn times Fn of x is equal to 0 for all values of x. And of course, if a bunch of functions are not linearly dependent, then we say that they are linearly independent, in which case you have only the trivial solution for S1, S2 up through Sn. Okay? Right, so determining whether a bunch of functions are linearly independent or not is not always easy. Like if you take this, for example, sine 2 theta at first doesn't look like it's going to be linearly dependent with sine theta cosine theta, but it is because of a trigonometric identity. So we have a tool that's used to determine whether a bunch of functions are linearly dependent or not. So definition. Let f1, f2, dot, 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 up through fn be functions whose nth derivatives exist. The Wronskian of f1, f2, dot, 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 up through fn is the determinant So you got to take the determinant of f1 of x, then f1 prime of x, then f1 prime prime of x, dot, 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 all the way down to the nth derivative of x, of f1, sorry, not x. Then f2 of x, f2 prime of x, f2 prime prime of x, dot, 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 all the way down to f2 nth derivative of x. Or wait a second, no, I'm getting this wrong. These need to be, these would actually be n minus first derivatives. There we go. And dot, 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 until you get to the nth function, and then you take its first derivative and its second derivative, and so on, until you get down to its n minus first derivative, and you take this whole determinant. This is called the Wronskian of f1 through fn. Okay, so theorem. If W, the Wronskian of f1, f2, dot, 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 up through fn is not zero, not constantly zero, then f1, f2, dot, 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 up through fn are linearly independent. So, of course, we're going to look at some examples. So, are the following sequences of functions, or I should say, is the following sequence of functions linearly dependent? So here's the sequence. First function is going to be sine x. Second function is going to be cosine x. We're going to determine whether these two are linearly dependent or not. So what we've got to do is take the Wronskian. So Wronskian of f1 and f2. In this case, we're going to take the matrix sine x, cosine x, because the derivative of sine x is cosine x. Then cosine x, negative sine x, because the derivative of cosine x is negative sine x. So you take this determinant. Okay, you do that by multiplying sine x times negative sine x, you get negative sine squared x. Then subtract from that cosine x times cosine x, so minus cosine squared x. So we get, this is negative sine squared x minus cosine squared x. Is that constantly zero? Well, no. In fact, this is just negative 1, because this is negative of sine squared x plus cosine squared x. So this is negative 1, which I'm pretty sure is not constantly 0. So that means that these two functions are indeed linearly independent according to the Wronskian. Let's take a look at just one more example of using the Wronskian to compute whether some functions are linearly independent or not. Actually, yeah, let's do it. So, same directions, determine whether the following functions are linearly independent. E to the x, e to the 2x, and e to the 4x. Just realized my angle is not ideal. That's a little bit better, I suppose. Right then, so to compute the Wronskian of e to the x, e to the 2x, and e to the 4x, we need the determinant of, let's see here, e to the x, then the derivative of e to the x is e to the x, then the derivative of e to the x is e to the x. So that's our first column. Then we have e to the 2x, the derivative is 2e to the 2x, and then the second derivative is 4e to the 2x. And then the third column is e to the 4x. First derivative is 4e to the 4x. Second derivative is 16e to the 4x. So we need to compute this 3 by 3 determinant. Those of you who have taken Calculus 3 already know how to compute a 3 by 3 determinant, I think. As for those of you who haven't, this is how you do it. So what we've got to do is go along the first row of this matrix, select the entry in the first row, and then set up a 2 by 2 matrix right next to it. Then take minus the first row second column and put a 2 by 2 matrix there. And then take the third element in the first row and take a 2 by 2 matrix there. And so then what should be in these 2 by 2 matrices? Well, what you need to get is you need to delete the row and column that contains e to the x. So delete this row and column, and then we get this submatrix here. 2e to the 2x, 4e to the 4x, 4e to the 2x, 16e to the 4x. That's what we're going to put here. So 2e to the 2x, 4e to the 4x, 4e to the 2x, 16e to the 4x. Then the next one, we're going to do the same thing. We're going to take the row and column that contains e to the 2x and just delete it and write down the submatrix that we get. So that'll be e to the x, 4e to the 4x, and 16e to the 4x. And then finally for e to the 4x, you delete the row and column that contains that, and you get just e to the x and e to the x as the first column, and then 2e to the 2x and 4e to the 2x as the second column. So every 3 by 3 determinant can be broken down into 2 by 2 determinants. Anyway, now that we've got this, we just compute these 2 by 2 determinants. So let's see here, we have e to the x multiplied by 32 e raised to the, okay, we need to add the exponents, so we'll get 6x minus 16 e to the 6x minus e to the 2x times 16 e to the 5x minus 4e to the 5x plus e to the 4x times 4e to the 3x minus 2e to the 3x. And then the only question left is whether that is constantly 0. Well, let's see here. This is going to be e to the x multiplied by 16e to the 6x minus e to the 2x multiplied by 12e to the 5x plus e to the 4x multiplied by 2e to the 3x then this becomes 16e to the 7x minus 12 e to the 7x plus 2 e to the 7x. 16 minus 12 plus 2 is just 6, so this is 6 e to the 7x, which is not constantly 0. And so what that tells us is that these three functions form a linearly independent sequence of functions, because the Wronskian is not constantly 0. Okay. So now, before we get into solving second order ODEs, we're going to have to introduce a little more terminology. Okay, so first of all, 2.1, second order linear ODEs. So recall that a ODE is linear if it can be written as function of x times nth derivative of y plus function of x times n minus first derivative of y plus dot 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 plus function of x times first derivative of y plus function of x times y equals some other function of x. Okay, so a couple of things to point out here. First of all, these p's, they have a name. All these functions, p0 through pn, these are called coefficients of the ODE. And then this one over here, this one that doesn't have a y or a derivative of y attached to it, this one is called the inhomogeneous term. Okay. So a linear ODE comes with coefficients and an inhomogeneous term, and it's just a linear combination of y and its derivatives with those coefficients as the weights equal to the inhomogeneous term. Now, as I mentioned before, this term has nothing to do with the homogeneous substitution. It's very unfortunate, but I can't change the terminology. So yes, this is what a linear homogeneous ODE is. So, definition. A linear ODE is homogeneous if its inhomogeneous term is constantly 0. So the constant function 0. So for example, y prime plus 6y equals 0, that would be homogeneous. So this is homogeneous. On the other hand, y prime prime minus xy prime plus 6y equals x, this is non-homogeneous. And of course, there's lots of ways that you can manipulate this to go further. First of all, it doesn't have to be first order in order to be homogeneous. You could make it y prime prime. You don't have to have constant coefficients in order for it to be homogeneous. You could have like an x squared here. And again, these things are still homogeneous. This one is still a homogeneous equation. This one is still a non-homogeneous equation, because it's all about whether this thing that doesn't have y or a derivative of y attached to it, if it's zero. Okay? So, for the moment, so I said already that the topic of higher order ODEs was too broad, so we had to restrict ourselves to linear ones. Now, linear ODEs is too broad, so we have to restrict ourselves to homogeneous linear ODEs for the time being. We'll get to non-homogeneous ones later, but for right now, we'll just concentrate on homogeneous ones. So there is a theorem. This is called the solution theorem for linear homogeneous ODEs. Or as I like to call it, STOLCH, because you abbreviate it as STLH. Anyway, the theorem is let Ly equals 0 be an nth order linear homogeneous ODE. Okay. If y1, y2, dot dot dot, yn are linearly independent solutions. Okay, so we have n many solutions, so it's the same as the order of the ODE. So if it's a second order ODE, we have 2 solutions. Third order ODE, we have 3 solutions, and so on. They have to be linearly independent. Okay? If you have this many linearly independent solutions, then the general solution is y equals c1 y1 of x plus c2 y2 of x plus dot 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 plus cn yn of x. In other words, what I'm saying is, if you have n many linearly independent solutions of a linear homogeneous ODE, then you can craft the general solution as just all the linear combinations of those. And then that is a very important theorem. That's why I'm abbreviating it as STOLCH. It's because we're going to be referring to it a lot. Okay. So that's pretty much all that's important for 2.1. Let's move on to actually solving these things. So 2.2, constant coefficient second order linear ODEs. So it turns out that second order linear homogeneous ODEs, for some reason the textbook, the name of the subsection is this, but it should really say linear homogeneous ODEs. In any case, second order linear homogeneous ODEs is still too broad, so we have to narrow it down to saying only constant coefficient ones. Okay. So, in general, a second order linear ODE always looks like function of x times second derivative of y plus function of x times first derivative of y plus function of x times y equals function of x, right? Okay, then if you say we're going to restrict ourselves to homogeneous ODEs, that looks like function of x times y prime prime plus function of x times y prime plus function of x times y equals 0. Then, if you say you have constant coefficients, that looks like a constant times y prime prime plus a constant times y prime plus a constant times y equals 0. That's the kind that we're going to solve today. Or at least we're going to start solving them. The truth is that there's actually a little more to it than can be covered in a single class. So here's the idea. We're going to you might not believe what I'm about to say, but often the way to do math is to just guess and then correct your guess in order to actually get to the solution. So at some point, someone looked at these types of ODEs and said, all right, I'm going to guess the solution, y equals e to the rx for some constant r. Okay, let's see here. So first of all, if you want to plug that solution into this ODE, then you're going to need a couple of derivatives of it. So r e to the rx, and y prime prime would be r squared e to the rx. You plug that in, you get a times r squared e to the rx plus b times r e to the rx plus c times e to the rx equals 0. You can factor out e to the rx. So you'll get a r squared plus br plus c times e to the rx equals 0. Well, e raised to a thing is never 0. Therefore, if the product of these two things is 0, then this thing had to be 0. So that gives us the equation ar squared plus br plus c equals 0. And this thing right here is called the characteristic equation of the ODE. So, how does this work? Well, of course, we're going to have to look at some examples. So, let's say we want to find the general solution of, okay, let's see here. This needs to be a second order constant coefficient linear homogeneous ODE. So let's take 2y prime prime minus or plus 2y prime minus 4y equals 0. All right, well, certainly that's an ODE. Certainly it's second order. It's linear and it's homogeneous because this is 0. And it has constant coefficients because we just have 2, 2, and negative 4 as the coefficients. So, we guess the solution, y equals e to the rx. We're going to need a couple of derivatives of that in order to study what that relates. In order to study the relationship between this function and this ODE, we need a few derivatives. That's what I'm trying to say. Okay. So y prime equals r e to the rx, and y prime prime equals r squared e to the rx. You put that into the ODE, you get 2 r squared e to the rx plus 2 r e to the rx minus 4 e to the rx equals 0. Now, you can factor out e to the rx, and I guess you can also factor out 2. So we get 2 e to the rx times r squared plus r minus 2 equals 0. And then that gives us the characteristic equation, r squared plus r minus 2 equals 0. So what this is saying is that if you have a solution of the form e to the rx, then r has to satisfy this quadratic equation. All right, no problem. A quadratic equation, we know how to solve that from high school, right? We can factor this as r plus 2, r minus 1 equals 0, and get two different solutions, r equals negative 2 and r equals 1. Okay. So then, let's think about what those two roots correspond to, because we're looking at e to the rx, right? So this gives us two different solutions. Let's call this RA and RB. YA is going to be e to the negative 2x. YB is going to be e to the x. Okay, so according to Stolch, according to our solution theorem for linear homogeneous ODEs, we have two solutions. As long as the ODE is second order and these are linearly independent, the general solution is just all the linear combinations of these. Okay. Well, it turns out that they are linearly independent. You can show that by taking the Wronskian and seeing that it's not equal to 0. So the general solution is going to be C1 YA plus C2 YB, which in our case is y equals C1 e to the negative 2x plus C2 e to the positive x. And that's the general solution of our second order linear homogeneous ODE with constant coefficients. Okay. And the truth is that every ODE is like, every second order linear homogeneous ODE with constant coefficients is like this. You take the e to the rx, you get the characteristic equation, which, by the way, I'd like to point out, the characteristic equation, if you don't factor out the 2 here, we get 2r squared plus 2r minus 4 equals 0. That's our characteristic equation, right? If you notice, that is exactly what you get when you replace the y with a 1, the y prime with an r, and the y prime prime with an r squared. And that always happens. So if you want, when doing your work, you can just skip that step of showing how e to the rx is being used as a guess to find the solution. So we just need to go right to here, this characteristic equation. And then by studying the roots of the characteristic equation, we can figure out what the general solution will be. Now, I am somewhat oversimplifying this because the characteristic equation, if you remember from high school, it's a quadratic. That means that it could have real and distinct roots. It could have a repeated real root, or it could have complex roots, non-real roots, that is to say. Okay? And if that's the case, if in those latter two cases, repeated roots and complex roots, we're going to have to do things a little bit differently. But we'll get to that in a future lecture. For right now, let's just concentrate on when the characteristic equation has distinct real roots. Okay? So let's look at another example. Let's say we have y prime prime plus 5y prime plus 6 equals 0. And we're going to try to find the general solution of this ODE. Okay, so you can do this whole song and dance with y equals e to the rx, but I'm just going to write y equals e to the rx implies the characteristic equation r squared plus 5r plus, this should be a 6y. Sorry about that. 6y equals 0 plus 6 equals 0. You can then factor that as r plus 2, r plus 3 equals 0. That gives us two different solutions. R1 equals negative 2, and R2 equals negative 3. And then those correspond to two distinct solutions of the ODE, y1 and y2. And then from there, the question is, are these linearly independent? If so, then the general solution is just C1 times this plus C2 times this. Answer is yes. They're always going to be linearly independent if you have distinct real roots, because e to a root times x and e to a root times x are only linearly dependent if they're the same root. Which means that we'll have to do something differently when we get to repeated real roots, but we'll get to that in a future lecture. In any case, the general solution is just c1 e to the negative 2x plus c2 e to the negative 3x. All the linear combinations of e to the negative 2x and e to the negative 3x. And let's do one more example. Of course, I'm going to give you practice with these, but at some point you might feel like this is beating a dead horse. The reason why is because it just always turns out like this. You always just find a quadratic and then look at its roots and then construct solutions, and then all the linear combinations are the general solution. Well, let's do one more example. Y prime prime minus 5y plus 6, or y prime, plus 6y equals 0. All right, so again, if you take y to be e to the rx, then what you get here is r squared minus 5r plus 6 equals 0. You can factor that. That factors as r minus 2, r minus 3 equals 0. And then you get two solutions here. One of them is 2, the other one is 3. These give rise to two different solutions to the ODE, e to the 2x and e to the 3x. And then the general solution is c1 e to the 2x plus c2 e to the 3x. And that is that. Let's do just one more. How about y prime prime plus 6y prime plus 8y equals 0? Well, again, y equals e to the rx gives us r squared plus 6r plus 8 equals 0. That factors into r plus 2, r plus 4 equals 0. That gives us two different roots, r1, which is negative 2, and r2, which is negative 4. That gives us two distinct solutions, e to the negative 2x and e to the negative 4x. And then those two are linearly independent, so the general solution is c1 e to the negative 2x plus c2 e to the negative 4x, and that is that. All right? So as I said, our next task is to be able to do this if the characteristic equation does not have distinct real roots. And that'll be the topic of our next lecture. In any case, that's all for today. See you in the next one.